So, okay, we are going to work with the semiclassical Einstein equations in order to find these quantum corrections to Schwarzschild metric induced by the quantum vacuum. The semiclassical equation, the semiclassical Einstein equation is this one here, you can see. And in our case, since we are searching for corrections to Schwarzschild, we are going to consider the classical part as 0. And then the quantum part is going to be the one associated to the vacuum contribution. So what we are searching for is the possibility of static and spherically symmetric solutions. We know that this is not the most general case, but we are going to consider these ansatz and search if there exist solutions of this kind. So the problem is that the quantum part of the stress energy tensor is in general a complicated functional. And in particular for our case, this is the static and spherically symmetric solution. One can see the Anderson paper of 1995. And one can see that this is a very complicated functional of the metric, which includes third and fourth order derivatives and also a numerical part. Okay? So our strategy to avoid this complicated problem is to considering the stress energy tensor as a variable of the equations instead of considering it for a particular background or a concrete expression. So what we will do is give an equation of state that will be for a particular case that will simplify the system, and these simplifying assumptions will be motivated as we will see later. So then what we will do is solving these semiclassical equations, and there will be equations of back reaction because we are considering the stress energy tensor as a variable. Okay. So, as I said before, we are searching for static and spherically symmetric solutions. So therefore, we assume that the metric has this form here, which is the most general one. And if we assume that the vacuum state respects these symmetries, the most general stress energy tensor will have this form here. No? It will be diagonal and will depend on the energy density, the radial pressure, and the tangential pressure. So therefore, if we introduce all this into the semiclassical Einstein equations, we will obtain a system of 3 equations, which are the anisotropic Tov equations, because we are considering the radial and tangential pressure a priori different, with 5 unknowns, which are the 2 unknowns of the metric and the 3 unknowns of the stress energy tensor. So therefore, we need 2 equations of state we have to impose in order to find a solvable system. And how do we select these equations of state? Okay, this is where it enters the assumptions that we have done in this problem. Particularly, we have considered the case of a massless conformal quantum field because this simplifies so much the problem. And as we will see now, in general, for a general field, we don't know which relations have this between the density and the pressure. But for this particular case of a massless conformal quantum field, we know that this relation between density and pressure is univocally fixed by the well-known trace anomaly, as it follows here. We know that in general, a conformal field, classically, the trace is 0, but in the quantum case, it's no longer true. And we know that the trace is given by this expression here, which is the trace anomaly, where here C is the Weil tensor. And these coefficients A, B, C, D here depend on which kind of field we are considering. In our case, we will consider as a first step the case of a scalar field. So the only problem here is that this final term here goes with the box R, includes derivatives of third and fourth order of the metric. And this is a problem because the system becomes not a second order system of equations, but a third or fourth order. And our strategy to avoid this is taking advantage of the intrinsic ambiguity for this coefficient d. Okay, there is an interesting ambiguity in the trace anomaly, and which depends on the renormalization scheme. So we choose the renormalization scheme such that this coefficient d is equal to 0, and therefore we can have this trace anomaly in terms only of first derivatives, of the first and second derivatives. Okay, so the other equation of state that we consider is the isotropic pressure. We are considering that the radial pressure is equal to the tangential pressure. This is a simplifying assumption that we do, and it's motivated by the fact that the result of Candelas in 1980. In this paper, he found that the expression of the stress energy tensor for the vacuum for a massless scalar field conformally coupled to a Schwarzschild background in the Bolwer state has the pressure of this field is isotropic near the horizon. And since we expect that the main quantum corrections appear near the horizon and far away from the horizon, the pressure and the density will be practically 0, we can assume that this expression here is verified in all the space, because we expect that our solution behaves in a similar way as this solution of Candelas. This is our particular simplifying assumption. Okay, so introducing all of this into the semiclassical Einstein equation, what we find is this system of equations to solve, which is the top equations, but with the pressure and density of the quantum vacuum. And this final equation here is the equation of state, which is, on the right hand of the equation, one can see the simplified trace anomaly that has been simplified using the top equations. Okay, in order to have it all in terms of the functions and not the derivatives. So this is our system, and our boundary conditions that we assume for this problem is that at the infinity, this metric has behaved as the Schwarzschild metric. And therefore, we impose that the metric has this form, which is the Schwarzschild known expressions, and the stress energy tensor is 0 at the infinity. Okay. So first approach to solve this problem is to solve these equations perturbatively. We can assume that we assume initially that the metric will behave in this way. We will have, if we expand it in orders of H bar, it will have the order 0, which is Schwarzschild, and then a first order in H bar, which is what we are looking for. And then solving the equations perturbatively, what we find is these expressions here these are the expression near the point r equal to 2m. So this expression here, one can see that all of them goes like behave as the Schwarzschild, the classical one, no? Plus a term which is the correction that behaves linearly with H bar. One can also, it's also remarkable that all these terms are divided by this factor here, f, which is this factor 1 minus r over 2m, which is very small near the horizon, and therefore this term here can compensate the small value of H bar. And therefore, these quantum corrections are significant near the horizon. We will talk more about this later in the next. Okay, so first of all, we are going to discuss the conclusions we can take from this corrected metric. The first one is that the coordinate singularity is shifted. It's no longer at r equal to 2m. Okay, instead the radial component of the metric goes to infinity at this point, not at r equal to 2m, but at r equal to 2m plus a factor that has this expression here, which you can see that this the square of H bar, which is the Planck length. So therefore it's shifted, but only by very short, very small term. No? And the main conclusion that we found is that there is no longer a horizon at this coordinate singularity, at this point r equal to r0. And why is that? Because the redshift, the time component of the metric, does not vanish at the singular point. Okay, in Schwarzschild we have that in r equal to 2m, GTT goes to 0 and GRR goes to infinity. But in this case, when GRR goes to infinity, GTT doesn't vanish. Okay, in fact, the time part of the metric, the redshift, is different from 0 for all values of r greater than r0. And therefore, this implies that the point r equal to r0 is a singularity of coordinates, but it's not a horizon, in the sense that time-like geodesics can go in both ways. Okay. So the problem of studying solving the system of equations in this way, this perturbative way, is the following: it's that near this singular point, the corrected metric is no longer it's non-perturbative, okay, because of this factor I mentioned before, 1 over f. One can see that for seeing an example. For example, the pressure. If we assume that the pressure behaves as a first order term plus a second order term, and we find these terms perturbatively, we find that the first order term behaves as h bar over f to the square, as I showed before, and the second one behaves as h square over f to the fourth. And we can see that near this point, in the limit of r tending to this singular point, the function f behaves as the square of h bar, and therefore one can see here that this f compensates the h bar, but in fact it compensates it in such a way that one can see that the term at first order behaves has the same order of the second order term, and therefore the perturbative hypothesis is not verified, and therefore this perturbative solution gives us a bit of intuition of the kind of conclusions we can have from the corrected metric, but it doesn't. It isn't a well approximation to the problem. So therefore, if we want more accuracy, we have to solve it numerically and find the exact solution. And this is what I'm showing here. It's the main conclusions can be seen from these two graphics. We can see here I have represented the cosine between the redshift we have found and the redshift classic, and one can see that when we are tending to in the limit of r tending to the singular point, it doesn't vanish, but instead the radial part, the radial component of the metric goes to 0. This point, that's why it's the singular point. Okay, but the redshift doesn't vanish. Okay. So apart from that, we have found that, as I said before, the singular point is shifted. It's not longer at 2m, but at 2m plus this term here. This number changes when comparing it with the perturbative solution, but quantitatively is the same. I mean, it's goes with the square of h bar. So we have found that the quantitatively properties are the same that I explained before in the perturbative solution. So the next step will be to study how the metric behaves beyond this singular point r equal to r0. Is it a wormhole, or is there any kind of singularity? So this is for solving this, we have to change the coordinate, because this coordinate doesn't behave well because of the coordinate singularity, and we have to find appropriate coordinates to trespass to the interior part. And this is the work that we are right now doing. Okay, so we don't have yet conclusions of this, but we expect to have conclusions in the short future. So finally, I will comment the summary of what we have done and the conclusions. So we have solved the semiclassical instant equations to study the corrections of the Schwarzschild metric induced by the quantum effect of the vacuum. We have searched for static and spherically symmetric solutions, which means solving the semiclassical Topf equations. We have considered the stress energy tensor, the quantum stress energy tensor, as a variable instead of computing it on a fixed background. And we have considered that the special case of a quantum conformal field, because in this case we can take advantage of the trace anomaly in order to define an equation of state that makes the problem solvable. And finally, the conclusions we have obtained from the calculation is that the coordinate singularity is shifted by the position of in the radial coordinate is shifted by a factor of the order of the Planck length, and in this particular point there is no longer a horizon, and therefore we can extend the metric beyond this point. And this is a work in progress because we are right now trying to extend the metric to the interior and describe his properties. So thank you very much for the invitation and all.
Thank you very much, Pau, for this interesting presentation. We have time for questions. If anyone wants to ask anything. Okay, we have a question by Daniel Sudaski. Please unmute yourself.
Hi, Paul. Thank you for your talk. First of all, let me say I agree with you that probably starting a perturbation expansion using coordinates that are singular or bad coordinates at the horizon is likely to be the cause of some of the problems you're encountering. But there is another issue that you mentioned that could potentially be the source of problems, which is that you motivated your isotropic choice in the equations of state on the Bolwer vacuum, which is a state that we know is ill-behaved, is not Hadamard at the horizon. So perhaps it would be a better idea to motivate whatever conjectures you want to do about the equation of state on some some state that is truly Hadamard at the horizon.
Yeah, thank you, Daniel, for your question. Yeah, that's true. And in fact, the reason why we motivate this like this with the Bolwer state is because we are searching for static solutions, which are in the static vacuum would be the choice. Logical choice would be the Bolwer state, but we know that this is not the most general case. In fact, we should consider another kind of vacuum and also the time dependence of the metric. But at the beginning, we were just trying to see if there exists these static solutions. So therefore, but we haven't yet finished the work. I mean, we have to extend to the interior, and we don't know in the interior if there is some kind of problem that comes from this point here, of considering staticity. But okay, for the moment, what we have found is consistent and it's static and it's a solution. But yeah, I know your point, and this is I think this is something we can debate if it's correct or not to consider this isotropic pressure.
Okay, thank you.
Thank you.
I have a comment. I think that so far the results that you're finding are consistent with other back reaction analysis in the literature. And have you explored the possibility, again, it goes concerning this isotropic pressure assumption. There are other approximations to the renormalized stress energy tensor which do not rely on isotropic pressures. And still they find this breakdown, of course, for fields defined in the Bolwer state, they find these non-perturbative effects near the horizon. So maybe it could be interesting to explore a wider family of equations of state that allow you to relax this assumption and seeing how how consistent the results are with these choices.
Mm-hmm. Yes, we have talked about this so much, in the sense that the logical next step would be this, not considering isotropic pressure, but considering that the difference between the radial pressure and the time-like pressure is given by some kind of expression that we can take from, there are some studies about this relation. Yes, this would be, I mean, this Candela's result motivates to think that they will be more or less similar, but maybe they are not equal, in the sense that it's a logical next step, to study the case of these two observables are not equal, but there is an expression of this difference.
Yeah, probably you've already thought about this so much, but it could be interesting to compare.
Yeah, we have thought about it, but we haven't yet started to approach this problem. But this is something we are thinking, yeah.